All right, guys, so I'm going to introduce to you our new unit today. We're looking at logarithms as the inverse of an exponential function. So back in grade 11, we learned about exponential functions. If you kind of think back, we did exponential growth, exponential decay, things like half-life, doubling, and all of that kind of stuff. So just to remind you, our formula that we used in that unit was the equation y equals a times b to the exponent x. Exponential functions themselves are able to be identified because x is in the exponent. And if I see x as an exponent and then a base of a number, that means that my function must be exponential. So look for x in the exponent and you'll know that the function is exponential. If b is greater than 1, so any value that's bigger than 1, we will be dealing with exponential growth. If it's between 0 and 1, we will be dealing with decay. Okay, y is our future value, a is our initial value, and then x can be calculated by doing the total time over the growth or decay period. So essentially I'm looking for how many times a growth has happened or a decay has happened within the given time period. All right, so we'll do kind of a review of a couple things and then we'll get into a little bit of new grade 12 material. So our first example is that an insect colony has a current population of 50 insects. It doubles every 3 days. So what is the population after 12 days? Okay. So here I have a current population, which is my A value, that's my initial value, of 50 insects. Yep. Yep, so we're just building on that and we're kind of recapping that right now, okay? 50 insects, it doubles every 3 days. What is doubles? What does that tell me about? Jonathan?
Times 2.
Times 2, and what variable is that in our formula? So is it the y, is it the a, is it the b, is it the x? The b, yeah, it's our growth factor. So it would be multiplying by 2, so b will be 2. Where does the 3 days and the 12 days come into play here? In the exponent, yes. So anything to do with time, I'm looking for how many times the population has doubled over that whole 12-day period. Well, if I have 12 days and it doubles every 3 days, then it must have doubled 4 times over that 12-day period. Okay, that's what x is. It's the number of times the doubling has happened in the given time period. Okay, y is my question mark. Okay, so this is just a really straightforward question that we had in grade 11 where we just subbed in the values and solved. Make sure you follow BEDMAS here. And we'll calculate from there. What'd you get? 800? Anyone else get 800? Yep, great. 800 what?
Insects.
Insects. So usually we end these guys off with an interpretation of our answer. So we'll say, therefore, after 12 days, the population of insects has grown to 800. Okay, any questions for that one? All right. How long until the population reaches 25,600 insects? Okay, so I'm still doubling. I am still starting with 50 insects. My y is my future value, so we actually have that value now. What we don't have is the total time. So we'll put that as part of our x, but we do have a growth period that we can put in as 3 days. So if my growth period is given to me in days, I would expect my answer for the total time to also come out in days as well. Okay, that unit of measurement will stay the same. So let's plug this into our formula here. Okay, does anyone remember how we solved, sorry, question, sorry?
I don't remember how, but can't you like divide 50 by both sides?
Yeah, so we would start by dividing out the 50. So I've got the base and the exponent now isolated on one side. 25,600 divided by 50. Alexandra?
Oh, I didn't get that. I was just going to say logarithms.
Yep, so the goal here is anytime we have an unknown in the exponent, I'm going to use logarithms. What'd you get, Fayak?
512.
512, thanks. Okay, so when I have an unknown in the exponent, we talked about how I can get that exponent out there if we do log of each side. Okay, I think most of you should have learned this in grade 11. There's also the guess and check method where you express 512 as a base of 2. But this tends to work well if we bring the exponent down in front. Okay, this is a logarithm rule that we're going to learn a little bit more about this year in this course. But basically for now, and when you were in grade 11, we just said this is a logarithm rule where if you have the log of something to an exponent, you get to bring down the exponent, and it will now be a multiplication. Okay, so let's just isolate now for t over 3. I'm going to divide by the log of 2. I'll get someone to calculate this for us, log of 512 over log of 2.
I got
9? Exactly?
Yes.
Okay. Okay, so it equals 9, and then I'll just multiply up the 3 on each side to get t by itself. Therefore, what? Can someone interpret this answer for us? What does this mean?
27 days for the population to reach 25,600.
Great. So therefore, it will take 27 days. Notice that we're getting that unit of measurement out in the same measurement that the growth period was in for the population to reach 25,606.
Wait, what do you mean 27 divided by 3?
No, because this is t divided by 3. So if I want to get t by itself, I have to multiply up the 3 on each side.
Oh,
Okay, any questions for that one? All right, we'll learn a little bit more into why this logarithm rule is possible this year. There's also a couple other logarithm rules that we'll be working with. So for your purposes so far, you've been introduced to log as a method of isolating for an exponent, basically. That is one thing that log is useful for, but there are some other connections that we can make with logarithms as well. Can I scroll? Yeah? Okay. All right, so I just want to quickly review over some exponent laws just to kind of set us up for the rest of this unit. Exponent laws are important here because logarithms and exponentials are connected in some ways, which you're going to kind of see in the second section here. So in order to understand some of the laws that I'll teach you in this unit, you have to kind of have a handle on some of the exponent laws. So really quick here, we have product rule, which says that if I'm multiplying two things with like bases, I keep the base and add the exponents. We have quotient rule, which says if I'm dividing two things with the same base, I keep the base and subtract the exponents. Okay, we have power of a power rule, or sometimes it's just called power rule. I keep the base and multiply the exponents. Okay, we've got the negative exponent rule that says if I have some x to a negative exponent, I can make it positive by moving it to the opposite side of the denominator. So currently here it's in the numerator. If I have the negative and I move that whole base and the exponent into the denominator, I can make it positive. Okay, and then there's the exponent of 0 rule, which says that anything to the exponent 0 is equal to 1. Yeah, so why is this true? Well, in one way, we can express it kind of like this. So if I have something divided by itself, what is anything divided by itself? 1. So in one sense, we know anything divided by itself is 1. Now, if we're on board with quotient rule here, we can also express this a second way. I can say that anything divided, any like base, I keep the base and subtract the exponents, right? Which gives me x to the 0. So if you agree with both of those things, then x to the exponent 0 must be equal to 1. Good? Okay. And then in grade 11, we also talked about inverse functions. So just as a reminder to you, inverse functions, we have this little notation where it looks kind of like an exponent of -1. So f, it's not an exponent. It's basically said as f inverse of x. And basically an inverse function does the opposite operations of the original function in the opposite order. So for any given input that you would put into f at x and you get an output, if I put that output into the inverse function, it would give me back the input. So the inputs and outputs are essentially switched for f at x and f inverse of x. So basically what we would be looking for graphically is I would see if this is f at x here, I would see all the points of f at x with x's and y's as swapped versions in f inverse of x. So you'll notice here that the point, for instance, 2, 4, on the inverse function is actually the point 4, 2. Okay? So literally we take all the x's and y's of f at x and we swap their locations, and that will actually give us the graph of the inverse function. Okay? So it's not a reflection, it's actually, well, it is actually a reflection, but the way that inverse works is it's a reflection over this diagonal line right here. So if you imagine kind of folding your paper in half over this diagonal line, that's where it's mirrored. So that's the line y equals x there. Okay? Algebraically, what we're looking for is, again, a function that does the opposite operations of f at x in the opposite order. All right, so we did this with functions, like we did it with quadratics in grade 11, we did it with square root functions in grade 11, and just like simple linear functions. I want to talk about the inverse of an exponential function here. So the process over here, if you're not quite sure how to do this algebraically, is that we need to replace the function notation that we see here with y. So I'm just going to start by doing that. Instead of f at x, we'll put y. That's step number 1. Okay, step number 2 would be to swap the x's and y's. So wherever I see an x, I will place a y. Wherever I see a y, I will place an x. Okay, and the reason that we do this is because essentially, in order to get the opposite operations in the opposite order, when I flip them and re-isolate, it actually takes care of that for me. So we'll start to isolate for it, and then in that process of isolating, we'll get operations in the opposite order and opposite operations as well. Okay, so now I need to re-isolate for y. And we know, based on our information from grade 11, that if I want to isolate for an exponent, what function am I using? Sorry? He doesn't know. What did we use when we were isolating for the exponent in our previous example here? Log. Okay, so in order to get the y by itself, I need to get it down and out of the exponent. So I think based on my previous knowledge here, we can use log. And that log rule again tells me that I get to take that exponent now and bring it down as a multiple. Okay, so here's what we've got. Okay, and we divide out the log of 2. And now this is what I have. Log of x over the log of 2 equals y. Now there's a little rule that I need to kind of pre-use here before we go over all of the log rules, just so that this makes sense. And it's this rule right here. It's called the change of base formula. And it basically says if I have the log of something over the log of something, I can combine this into one logarithm where the value of the log on the bottom, which in this case would be 2, becomes what we call the base of this logarithm. And the value on the top will be what we're taking the log of. So the value on the top for this one is x. So don't worry too much about this just yet, but in order to get to this last step, I needed to show you that little rule. I can combine this into one logarithm. It says y equals log base 2 of x. And then the last step here would be to replace your y notation with function notation. So it says f inverse of x is equal to log base 2 of x.
Then where'd you get the log 2x from?
Okay, so I'm just using this change of base formula to go from here to here. So the base will come from the log on the bottom, and then this value will go into the logarithm, so what we're taking the log of. Sorry?
Let's say you were to plug something in for the x because they're too small. Does that mean like it does something else? Like,
Yeah, so we'll unpack a little bit more like what logarithms are asking us to do. You can calculate things like this on your calculator, but hold off on that for now. I just want to observe what the graph of this function looks like. But yes, this does impact calculations that we'll make with logarithms for sure. Okay, so this is our function. I want to just look here and see, using some of the key pieces of information for these graphs. You may have graphed more in your table of values, but if I have 3 major pieces of information for an exponential and a logarithm, I should be able to get the general shape of that logarithm and exponential. So this is how I usually teach my grade 11s. If you were in a different class last year, you should have done something similar. Maybe you would have used a few more points. But if we have the x equals 0 and the x equals 1 point, and I plug them in for x in my function here, I can get 2 points that have x and y coordinates. So if I sub in 0 here, I get 2 to the 0, which we know is 1. And if I sub in 1 here, I will get 2 to the exponent 1, which gives us 2. That gives us 2 points on our function. And yeah, Alexandra?
What does HA mean?
Horizontal asymptote. Does anyone know where the resting horizontal asymptote lies for a regular exponential function that has no transformations? So for a regular exponential function with no transformations, where does the horizontal asymptote lie? Liam? X-axis, yep, or the line y equals 0. Okay, if we have transformations like shifts up and down, it will move with that. Okay, so I'm just going to pencil that in here before we do the inverse function. This is the asymptote of the function. And if I know where that is, I'll know kind of where my graph curves around. And then I have 0, 1, and 1, 2. So given my previous knowledge of exponential functions, just to remind you, exponential functions can take on only a few shapes. They can be growth, they can be decay, or it could also be vertical reflections of those things. What does this one fit into? What shape out of those 4? The first one, yeah. So my graph is essentially just curving up and through like so. And I'm just going to label that as f at x equals 2 to the x. Yes, so make sure you're not crossing over the asymptote and you're not touching the asymptote. Okay, now the inverse function, we just talked about how the inverse function has the same x and y coordinates as the original function, but they're swapped versions of one another. So this point, instead of 0, 1, becomes 1, 0. So I'm literally taking the x's and making them the y's, taking the y's, making them the x's. And this point becomes 2, 1. Any guess as to what the horizontal asymptote would become?
Become the y-axis.
Yeah, actually it will become the y-axis, which is the line x equals 0, which is a vertical asymptote.
Wait, can we explain what an asymptote is again?
So an asymptote is produced by restrictions on our function. And basically it's just kind of like an imaginary boundary of our graph that our graph will get infinitely close to, but it won't touch. So the idea is this one has a horizontal asymptote at y equals 0 because there's nothing that I can plug in for x that will give me a y value of 0 or a negative y value. So you'll notice that there's no part of the graph that's down in that lower area there. So like if I plug in 0 for x, I'm still getting a y value of 1. If I plug in a negative for x, I'll just get a smaller decimal. But I can't plug in anything to that function to get a y value of 0 or even a negative y value. That's why that ends up happening here. Okay, so let's graph it out and see what it looks like. So this is now a vertical asymptote at x equals 0. And we have a point at 1, 0 and 2, 1. And if I've done it correctly, it should kind of look like it is folded over this diagonal line y equals x. Okay, so there's the line of reflection there. So if you can imagine, our graph will kind of look like this. Okay, and then you can label that as f inverse of x. Oops. Okay, so this is what the inverse of an exponential looks like. This is what we call a logarithmic function. So for now, so far we know with logarithms, they help us isolate for exponents. They are the inverses of exponentials. We kind of know this like little change of base formula up here. So we'll continue to unpack this as the unit goes along. Okay, any further questions for this before we continue to scroll? Okay, so I want to just take a look at x-intercepts and domain and range for some of these things. So the x-intercept for y equals 2 to the x, or f at x we said. What is the x-intercept? Look up at your graph there. Where does it cross the x-axis? It doesn't actually, yeah, so there's none. The y-intercept is the point where x equals 0, and we have that actually in our table of values above. It's 0, 1. What is the domain of this function? Let's use interval notation. What would you guys say for domain here? Sam?
So it would be negative infinity to infinity.
Yeah, you're right. There are no x's that I can't plug into my function. Yeah, Alexandra?
Doesn't it cross the x-axis at 1, 0?
That's the logarithmic function. We're looking just at this blue function first. What about the range for the blue function? How would I say the range?
The domain's
Jonathan?
down, right?
Domain is left and right.
It'd be
Jonathan?
0 to infinity, round brackets.
Yes, so 0 is not included because at a y value of 0, x, there's actually a vertical or horizontal asymptote, sorry. So when y is 0, that function's undefined, but beyond that and toward infinity, our function is defined for all of those y values. And we said the asymptote was at y equals 0. Okay, let's take a look at, in particular, I'm interested in how domain and range change for the inverse function. So x-intercept. Alexandra, what's our x-intercept for this one?
1, 0.
1, 0, correct. Okay, y-intercept. Looking at the red function now here. There's none because there is an asymptote on that axis. What is the domain of this function?
Negative infinity to infinity. No, sorry, think about the range, sorry. It would be 0 to infinity.
0 to infinity. Good. And range. Good. And we said the asymptote above is x equals 0. So what do you guys notice about the connection between the domain and range of the original function and the domain and range of its inverse? Yeah, so these are actually essentially inverses of one another, right? The domain becomes the range of the other function, and the range becomes the domain of the inverse function. Okay, so the logarithmic function is the inverse function of the exponential function with the same base. Okay, you'll also notice that when you have no x-intercept, that results in no y-intercept of the inverse function, and these are reverse points of one another. Cool. All right, so a couple important things with logarithms. Based on our sketch above, the function is only defined when x, as we said with the domain up here, when x is greater than 0, okay? And not even equal to 0. So x can't be equal to 0 here. So only defined where the domain is from 0 to infinity. So x must be greater than 0. Okay, and someone was asking me about like what this means calculation-wise. Basically what this question is saying is that y, the answer that we get out from that logarithm, or the output of the logarithm, y is going to be the exponent to which the base, which is b, must be raised to give the value of x. Okay, so what does this mean? Well, it means that when I calculate a logarithm, the answer that I actually get out for that is an exponent value, which is why we can use logarithms to solve for exponents. So the solution to a logarithm is always an exponent. The logarithmic function is most useful for solving unknown exponents. Okay, so because logarithms give us out answers that are exponents, of course it's going to be very useful when we have an unknown in the exponent. And I introduced to you guys, or your teachers would have introduced what we call a common logarithm. So the common logarithm is stored in your calculator. It just looks as a regular log looks. So you actually won't really see a base. You won't see this little base b in there. But it's actually kind of one of those understood things in math. So it's called the common logarithm. Okay, they are logarithms with base 10, and it's kind of just like one of those understood things. So a couple of things that you guys already know that are understood things in math is like when I have the value 2, what's the denominator of this value? Technically is over 1, but we don't write that, right? It's kind of one of those understood things. Another thing that you guys already know as like an understood thing is if I have an x, what's the coefficient of this x? 1, right? So that's kind of one of those other understood things. Another one, this is maybe testing your grade 11 knowledge. What is the rational exponent that this root represents? 1 over 2, and that's because we understand that if there's no value in front of this root, that it's a square root, and that there's an exponent of 1 on here. So we know that this could be expressed as well as a value of 1/2. So all of this to say, basically, is that this is kind of another one of those things where it's a common logarithm because it's a logarithm that we use often. You'll see a lot of systems that we've developed as humans with bases of 10, like pH is one of those systems that has bases of 10. The Richter scale is another one of the things that we say, like the severity of an earthquake, it's measured by a base of 10 system. So if you see a regular logarithm, log of something, and you don't see a base on it, you are going to assume the base is 10. The calculator also stores it as the regular log button in your calculator, and that actually is a log with a base of 10. Okay, quick 2-minute break. All right, so I'm just going to show you how we can switch between exponential and logarithmic form here. Now this is for an exponential or logarithmic expression. If I'm solving for an inverse, I have to use this method that we used above. But if I'm simply switching between the forms, I can kind of rewrite any exponential in logarithmic form or vice versa. So if I see some value y is equal to some base b to the exponent x, I can express this as a logarithm or in logarithmic form. So the logarithm will be equal to the exponent x. The base of the exponent becomes the new base of our logarithm, and the answer to b raised to the exponent x will be inside the logarithm. Okay? So this is the exponent. This will be where your base was in your exponential, and then this will be the answer that you get out. Or in other words, like the output of that exponential question. Okay, and then similarly, if I want to switch something into logarithmic form, the base is the base of what I'm going to raise to some exponent. This is the exponent right here that we see. So it's b to the y, and then this is actually the output that we get from that. So it will be x equals b to some exponent y. Okay, so that's basically how we'll kind of switch between the forms here. So it works a little bit better if we have some numerical examples. So I'll show you in a second. Okay, so if I'm writing this in logarithmic form, the base is whatever the base is of the exponent. So that will be the base of my logarithm, log base 3. The exponent is the answer to that logarithm. So the exponent is actually going to be what we get out on the other side of the equal sign. And this is the original output of what I got from 3 to the exponent 4. That will be in the logarithm here. So log base 3 of 81 is really asking me how many times or what exponent do I need to raise 3 to in order to get 81. So 3 times itself how many times equals 81? Well, 3 times itself 4 times equals 81. So that's the idea of logarithms. Can someone try this one for me? Let's put b into logarithmic form. No one feels confident enough yet? Okay, what's the base?
4.
X is the base, 4 is the exponent, so that's what I'll get out from the logarithm. Okay, this is the base, right? It's raised to the exponent 4. That will be the answer we get out from the logarithm. Pierce?
Oh, log x h equals 4.
Right, so we'll say log base x of h equals 4. Perfect. Okay, anyone want to give C a shot? What's the base? So where's the exponent?
Or 8.
Okay, yeah. So log base 8, the exponent will be the answer that we get out here, so -2. And it will be log base 8 of 1 over 64. So what exponent do I need to raise 8 to in order to get 1 over 64? Well, the exponent that I need to raise 8 to get 1 over 64 is -2. That's what the logarithm is asking me. Okay, let's keep going here. Does someone want to try this one for us?
Wait, can we go back to the last one for a second?
Yep.
Log 8 equals -2.
So find the base and the exponent. The base part of that becomes the base of your new logarithm. The exponent is the answer to the logarithm. Okay, and then there'll only be one thing left over, so that will go inside the logarithm. Pierce?
Oh, for
Great. So log base 10 of 10,000 equals the exponent, which is 4. And I actually don't have to write base 10 because I know when I just write a regular log, the base 10 is understood. Okay? So we would actually write this as log of 10,000. And you can actually check this on your calculator. So if you type into your calculator log of 10,000, it's actually going to give you out 4 because 10 raised to the exponent 4 is 10,000. That's the idea of the logarithm. Alexandra?
If we forget to make the log to the base thing 10, will we lose marks?
I would say you need to get used to doing that. That would be like equivalent to you saying x to the exponent 1. We want to kind of get away from doing that. So I would say, yeah, you definitely don't want to leave that in there. Okay, so try to practice with that. Okay, we just talked about this. What is a root as an exponent? Not 1 over 3, but 1/2, right? A root I can express as 1/2.
I thought it was that's
Oh. And how do I express this as a logarithmic expression now? Log, what's the base? Pierce?
Log 9.
Log of 9, what's the base of the, actually no, sorry. Are you meaning log base 9?
Log is the base 9.
Okay. It equals what?
1/2.
1/2, so it's log base 9 of 3. So what exponent do I need to raise 9 to get 3? Well, the answer would be 1/2. Awesome, so we're gonna kind of use this within like other solving steps that we need. So it's good to be able to switch between the forms depending on what you need to solve for, especially if your unknown is up in an exponent. Or if you have an unknown inside a logarithm, it can be helpful to switch up the other way. So we do exponential form. So that's what we'll show here. So we're going to write these in exponential form. Does anyone want to give A try for us? Jonathan?
36 equals 6 squared.
Yes. So this should actually make sense, right? We know 6 squared is actually 36. So the base becomes the new base of our exponential. The answer to that logarithm is the exponent of the base, and then we'll get out 36. That's awesome.
So that's just doing the opposite of what we just did?
Yes. Yeah, exactly. Okay, and then graph the function in part B. So I'm looking for what this function's exponential function would be. Now, yeah, sorry? 10, no, where does the squared come from?
Oh, wait, no, not x.
Okay, so 10, what's the exponent?
Y.
Y equals x. Okay, now I wanted to show you guys this because there's a difference between finding an inverse function and switching into exponential form. When I actually want to express this as a function itself, the inverse to this function should actually be y equals something to do with x, right? So this one is not quite isolated in the way that we would need it in order to graph a function. So inverse and switching between exponential and logarithmic form is a little bit different. If I were to actually state the inverse of this function, the inverse of this function comes from the function y equals 10 to the exponent x. These are, again, two different ways of expressing this. Jonathan, did you have a question?
How'd you get 10 from that equation?
So the understood base on this logarithm is, it's a common logarithm, so the understood base should be 10. Yeah. Okay, so this is switching between exponential form and logarithmic form, but this is the actual inverse function. So if I'm looking to actually graph the function that is associated with that log to the base 10, I would be graphing y equals 10 to the x. So if I use my method above to graph this function, I find the 0 point, I find the 1 point, and I will find where the horizontal asymptote rests, which we said is usually at y equals 0 if there's no shifts happening. So 10 to the 0 is 1, 10 to the exponent 1 is 10. And this asks me to graph the original function here, so it doesn't actually ask me to graph the exponential function, but the function y equals log of x I can actually get from these points, right? So if I swap this around, I can get the points for log of x. And that becomes the vertical asymptote at x equals 0. This is the function that I'm going to graph here. But I was just showing you how we can get that from the original exponential function. Okay, so the logarithmic function that we had in part B crosses at 1, 0, and, or sorry, that should say 10, 1, not 10, 0. And 10, 1. Okay, so that is actually the graph of the common logarithm there. Okay, last little part, this one will be really quick. Can I scroll off of this? Everyone has this down? No? Okay, I'm just going to show you kind of how to evaluate logarithms. Let me know when I can scroll. Good? Okay, evaluating, there's a couple ways that we can evaluate. This would be like if we didn't have a log button on our calculator. The rule is that if I can express things with common bases, then their exponents must be equal. So if I switch this logarithm into exponential form, this would be 5 to the y equals 125. So switching to exponential form, and if I can create common bases on both sides here, I know the exponents are equal. So the question is, 5 to the exponent what equals 125? 5 to the exponent 3. So by my rule up here, if I have two equal bases, then their exponents must also be equal. So what can we conclude about y? Yeah. If 5 to some exponent equals 5 to the 3, then that exponent must be 3, right? So we must assume that y equals 3 here. So that must tell me that log base 5 of 125 is actually equal to 3. Okay, the question that I'm really asking here is 5 raised to what exponent equals 125? That's the answer to the logarithm. So here y equals 3. Okay, another way that you can show your work to calculate logarithms without a calculator would be to express this value that's inside the logarithm as a base of 2, or as whatever the base is of your logarithm. So in this case, does anyone know how I can express 2 to equal 16? So 2 raised to what exponent equals 16? 4, yes. So I can say 2 to the exponent 4. And then by our logarithm rules, or actually by this logarithm rule that's up top here, any log that's expressed where the base is equal to this value here is actually just going to end up equaling the exponent. So I have it now set up in this format where this base and this base are the same. This is 2 and 2. So by the rule that we see above here, y is actually just equal to, oh sorry, not 2, to 4, to the exponent. Okay, and I'm just using this rule in order to solve that. Okay, so if I can express with the same base as the logarithm, I'll just have my answer equal to the exponent. So this works when I can create like exponents and like bases, or sorry, not like exponents, but this works when I can create like bases. If I can't, I'll need a calculator to help me with it. Okay, so we're just going to practice with those rules above. So I'll show you each one of them. So for this one, I'm going to express this in exponential form. 10 to the y equals 1 over 1,000. So what I would like to do is I would like to represent the value 1 over 1,000 as a base of 10. So 10 raised to what exponent is going to be 1 over 1,000?
10 to -3.
Yeah, -3, you guys are right. So therefore, if I have 10 to the y equals 10 to the -3, therefore y must be equal to -3. Okay, so that's the like bases method. I can also do this if I try to get whatever's in the logarithm expressed as the same base of the logarithm. So in other words, I have to express 1 over 81 as some base of 3. Okay, just as a little hint, if it's 1 over a value, it's probably just telling you that that exponent is negative. So I could just think to myself, 3 to what exponent gives me 81, and then I could use the negative version of that if it's 1 over 81. So 3 to what exponent equals 81? Is it 4? Yep, that's right. And because it's 1 over 81, it's actually -4. Okay? So if you see 1 over, just use the denominator value and then make the exponent negative. Okay, so therefore, by our rule above, y equals -4. Yeah. So if I can express that logarithm with the same base as what's inside of it, then I get to just say the answer is the exponent. Great. So I'm using this rule above here, and it says if I can express my value inside my logarithm with the same base as the logarithm, so if I can make these match, then it must be equal to the exponent value. So if I can create common bases there, my answer is just equal to the exponent.
Something that both goes into 2, and something that is into 2.
So this one, I expressed 1 over 81 as a base of 3 because the base of my logarithm is 3. And my rule tells me that if I do that, then the answer is just equal to the exponent. Okay, we'll unpack this a little bit more as to like why this rule is true.
I still don't understand where you get -4.
Okay, so I'm just going to cut the video off here, but actually maybe not, I'll keep it rolling. Okay, if we use our grade 11 knowledge, I have logarithm in front of something, so I'm allowed to bring down the exponent, right? That's a log rule that we learned in grade 11. Log base 3 of 3 is saying 3 raised to what exponent equals 3. So 3 to what exponent is 3? Well, 3 to the 1 is 3, that's right. So the answer to that logarithmic expression is 1. So what's the answer here? -4 times 1. Well, it's -4, okay? So for our purposes here, these bases will always match if you're using this method. So you have to make the bases match in order to use this method. So it's not going to happen where you have 6, right? If you can't create like bases, then we're calculating using a different method. So we'll talk about that later. Okay? But for our purposes right now, you have to either be able to create like bases here or like bases here in order to use either one of these methods.